So in this video, we're going to try to apply the alternating series test to help us determine whether the series converges. Now on this left-hand side, you might notice that I've crossed out or diverges, and that's because the alternating series test can only tell us whether a series is possibly convergent. It can't tell us anything about a series if it diverges. So let's take a look at this series that we're given. It's cosine of n pi all over n minus 2/3. So the first thing to do if we want to apply the alternating series test is, well, make sure this is an alternating series. If we take a look at what we have in this series function, well, in the numerator, we have a cosine of n pi. We don't see sort of the other minus 1 to the n, minus 1 to the n plus 1 type terms that we see a lot in these alternating series. But it turns out that this cosine of n pi is actually a minus 1 to the n in disguise. So let's take a look at this cosine of n pi for a moment. So if we start looking at different values of n, say you make a column of n versus cosine of n pi, let's see what shakes out of this. So if n is 1, 2, 3, 4, etc., let's see what these values of cosine of n pi are. Well, when n is 1, we have cosine of pi. When n is 2, we have cosine of 2 pi. When n is 3, we have cosine of 3 pi. When n is 4, we have cosine of 4 pi, and so on and so forth. And well, if we remember a lot of our unit circle properties about sine and cosine, a cosine of pi is equal to minus 1. Cosine of 2 pi is equal to a positive 1. Cosine of 3 pi is minus 1. Cosine of 4 pi, that's a plus 1. And we could keep doing this if we'd like. But hopefully this convinces you that, well, actually a cosine of n pi, that's equivalent to the same thing as a minus 1 to the n if we're putting in positive integers n into that. So this is actually an alternating series. It's just that the minus 1 to the n term is written in this cosine of n pi way. So for an alternating series, the next thing we do is try to pick out the positive terms in the series, as in the terms that are not causing any alternations in sign. And in this case, it's going to be all the remaining terms. So we have a 1 over n minus 2/3. And what we should do is also make sure that we check this denominator so we're not getting any alternations in sign from this. And well, for this series, we're starting from n equals 1, we're going to infinity. If n equals 1 here, that denominator is still going to be positive. If n is 2, the denominator is positive. So it looks like this bn term will always be something strictly positive when n is greater than or equal to 1. So for alternating series now, if our alternating series positive part satisfies 2 criteria, then we can say that this series overall is convergent. So the first criteria is we take the limit as n goes to infinity of the positive portion of the series. So that's our bn term, so 1 over n minus 2/3. As n goes to infinity, if we look at this, well, that denominator has an n in it. If n's going to infinity, this denominator is getting very, very large. Whereas in the numerator, this denominator is still a finite number. So that numerator, again, that's some finite number. So we're in this situation where we have a finite number sitting on top of a number that's just growing and growing and growing. Overall, this limit is going to look like 0. So that limit does indeed approach 0 in this case. The second criteria is we need to show that these bn terms are all decreasing. We can do this a couple different ways. We could use some algebra. We could do some derivatives. Let's just practice some differentiation here. So the way in which we can show this is decreasing is we want to take a derivative of our series positive terms and basically show that this derivative is negative for x values greater than 1. And why we want these x values greater than 1? Well, that's just because our series goes from n equals 1 to infinity. All right, so let's start off with this derivative. First, making sure we're calling the same thing our function f of x. So our f of x function is basically going to be the series positive terms that we have up above, except instead of integers n that we want to put into this, we want to put into a real variable. So we will just basically replace the n's by x's here. So you have 1 over x minus 2/3. And to practice some chain rule stuff and avoid a quotient rule, I'm going to rewrite this with a little bit of algebra. So we can rewrite this as x minus 2 over 3 raised to the minus 1 power. And the reason for doing that is, well, instead of doing a quotient rule, we can do a chain rule type differentiation, also just to practice a little more algebra. All right, so let's take a derivative of this. So if we take a derivative, we see we have this x minus 2/3 raised to the minus 1 power. So we can do a power rule type differentiation, so that minus 1 comes down. Then we have what was originally there, x minus 2/3, but instead of having it raised to the minus 1 power, we subtract 1 from that, just like we would a power rule differentiation. So we get this is now to the minus 2. And then finally, we differentiate by what's inside of the parentheses. So the derivative of x minus 2/3, well, that's just going to be 1. So this derivative, what it looks like now, is this derivative is basically a minus 1 all over the quantity x minus 2 over 3 squared. So again, what we want this derivative to be is we hope to see that it's less than 0 for all x values greater than 1. So let's look at this. Well, in the numerator, we have a minus 1. That numerator is always going to be something negative. If we take a look at the denominator now, we have, well, whatever x minus 2/3 is, and x is always going to be a positive value greater than 1. So that numerator inside of parentheses is positive, but then also we're raising whatever that number is to a second power anyways. So whenever we square a number, it's always going to give us a positive number back. So that denominator is always going to be positive, which means because of this minus 1 in the numerator, this overall derivative is always going to be negative. So it's always going to be negative for x values greater than 1. So in this case, this satisfies the second piece of criteria. And similarly, we've showed already that limit goes to 0. So by alternating series test, this series is convergent.